bidirectional converters, where it is converted to FPGA or electric vehicle application. Right. So moving on. Yes.
What way system done by directions stuff which part of hardware with analysis of motion. Modeling hardware yes. But rapid prototyping of bidirectional DC control. Right? So okay, from that perspective you are that.
Right, so our outcome statement is to design a bidirectional controller using FPGA loop to demonstrate the rapid technique. Moving on, there are different types of controllers available in the market that are mainly some of them are multi-law controllers, fuzzy controllers, high-dimensional serial networks, and sliding mode controllers. These are some of the benefits that you can offer. We have currently chosen that control because we were targeting it on applying an algorithm, and then obviously this algorithm can be improved by using our system, right? Moving on, talking about the need for hardware for control and testing. This related testing of and there are also this hybrid group is also using bioelectronics converters modeling platform to rapidly deploy and prototype for testing in the industry. It's used starting when implemented in the industry and there are extensive techniques. Like for example, is deploy the different control algorithms using test them against each other. Moving on. So this is a block diagram of what we are able to do. There's a various DC-DC converter which is powered by the DC battery. Then there is a DC to AC converter which is needed that we have got tested with this with the converter. And then obviously there's a motor encoder. Like this is a whole electrical system that there is. Where the controller for this DC bidirectional converter is what we have.
This is basically a compact view of the
whole. Yes. Right, so these are some of the configuration steps for FPGA NU. So first of all, we set up with the FPGA design. So the MATLAB version that we have used is 2017. And this is simulating the processor on the model. So this is just developing this simulation of whatever the fusion in this particular example we have used the buck controller, and then we have tested the results that we have, and once all of that is done, we set up the SDL workflow advisor, where it starts with all the science and data here, bind and it uploads all the files, and then it starts building on the FPGA, right? And in order to make sure that the data conversion is appropriate, we make use of kind of converters that are different types available in MATLAB. So we have mainly use of this one. Moving forward, okay, so once we are the block is generated in this form, we pick up this block from this model and inserted into our own model. So now this converter is in our model, and then we can run it. Before running it, we also have to upload the file that has been created. And once that is done, other accounts that are received, then we can compare with the old results. And moving on.
Right, so here I said it is study of the application to 1.2 case the first of the let's go
Sir, can you hear us properly now? Your echo abhi bhi hai. Sir Ahmed, are you there?
Shall we continue? He's not responding.
Record to have recording.
But अगर echo आ रहा है तो फिर recording भी continue.
Right, so जो हमने primary study conduct किया that is for the first of all the non-ideal DCDC non-isolated bidirectional converter. उसमें फिर हमारे पास we have converter design and its simulation, and then the controller design and its modeling. Then the controller is deployed on the FPGA, so that we have created the FIL setup, and finally I will be talking about the analysis result of that setup. So this is all of these four main parts are for the non-ideal DC to DC non-isolated bidirectional converter.
Is all after your meta-evaluation or
so what happened after meta-evaluation is that this is a couple of things in regards to the parameter to be done in the context of electric vehicles, so that we did, and apart from that we was synchronous certification, so that we also incorporated. So some of the changes that we incorporated in this model, also most of this part was in evaluation, but the changes that we did afterwards, uske jo corresponding results are that we right. So this is the big picture of what the converter looks like, a non-ideal DC non-bidirectional converter. So we have the usual B battery and the B bus, which is the low side voltage and the high side voltage, and then the MOSFET, and also the non-linearities which are accounted using the series resistance PSR for inductance, like both of the capacitor. And for the power flow, as far as the power flow, when the converter is working in the buck mode, so the power will be flowing from B bus to B battery, and in the case of the boost mode, it would be flowing from the B battery to B bus, where battery would be discharging, and in the case of buck mode, the battery would be charging. Right, so this specific schematic corresponds to the simulation model that we had. So above is the simulation model, and below is all the entire control part, that is FPGA compatible or STL compatible. So the entire converter is running on the simulation, and the control part that is defined using this sub-block writer closed loop control is running on the FPGA, and this FI block was generated corresponding to the above block, and then we were running on it in the loop with the FPGA in the real time. This is the close-up picture of what the controller looks like. So we have the reference voltages, and then we have the buck boost selection mode, because in the simulation we were manually controlling whether we want to charge or discharge the battery. So for that we have the buck boost selection mode, and then we have the rate transition and the data type converters, because between the FPGA and the simulation environment we had to use the appropriate block in order to allow the FPGA to interface with the simulation and to correspond the data with valid data types. Yes. This block right here, buck boost selection. So it has to be manually. We could also design a step response, but we actually did and a step response from one of the test cases as in the load variation. So उसके results हम लोग share करेंगे, but manually it was being done. Right, and this is the close-up picture of this control block right here. So we have the usual PI controller designed separately for the boost as well as the buck, and corresponding to them we have the corresponding HT compatible. So for using the 64 game block is used because the HT compatible compensated using, I think it was 6 bits. So there is also additional logic of the cycle generator which requires the gain of the 64 block, and then there is corresponding switching compared and corresponding to whether we are working in the buck mode or the boost mode. So when the battery will be charging and if the battery will be discharging against the motor, the converter would be working in the boost mode, and this boost controller PI would be active. And in the other mode where the battery would be charging using the buck in the buck mode, this buck controller PI would be active. Inside these blocks, we have simple PI gains and the integrator and the differentiator for the usual PI control. Right. So once we had defined the schematics as well as the model, the next step was to mathematically model it in order to calculate the PI gains for the converter. So this is the for most part we have used references in order to obtain this state space representation of the non-ideal bidirectional DC-DC converter, and this is the small signal model that we obtained from one of the book. That Dr. Ahmed Usman suggested. So उसमें से we picked up this state space representation of the small signal model, and then we for the input delta x and delta x2, which are the state space variables of the output capacitor voltage and the inductor current, and then the corresponding output voltage, which is the V out. This is still not isolated as small signal model. For small signal model, we can find small variations with it in correspondence to the duty cycle. For example, if we want to start cycle, we have to see those small variations are in duty cycle. Output voltage is still affected. So both has used this approach where it's still the non-ideal, non-isolated bidirectional converter. You can both use this approach to model the small variation of that using this specific.
So what is the role of this transformer? Is it 1 to 1
I think it was modeling the small variation of the duty cycle, because D prime is the D prime.
So the question is, why all of a sudden there is a what are these shortfalls or constraints in the non-isolated versions where we can't read as a clear and may transformer could be used.
And so actually for that, as I said in my if you want the control variable duty cycles to using the transfer function, which is in the form of P out voltage, where the output voltage is defined as a correspondence with the change in the duty cycle. So when we are doing do the steady state analysis of the previous model that we had, in that we are obtaining the D in terms of meter squared in a non-linear mode, basically. So non-linear fashion. So in order to avoid this non-linear, we have to linear model in order to do so. We have to perform small signal analysis. For that purpose, we have this. So these are two state space variables, so in correspondence with the capacitor voltage and the inductor current, and then we have the output capacitor voltage that we have to control. That is how we all this is the final. Right. Once we have this. So these state space representation, the next step is we can use two matrix identities to obtain the final transfer function G of S, which is basically the output voltage of the capacitor with respect to the change in the duty cycle. So this is the final transfer function as per that identity. So that identity can be used to derive different transfer function as well, but since we have chosen our control variable to be duty cycle, so this was the specific matrix identity that we had to use in order to obtain the final transfer function, which is in regards with the output voltage to be capacitor voltage and input to be the variation in the duty cycle. Right. So once we have this transfer function, the next is so this was all of that was performed in the case of the boost mode, where we usually what we do is we neglect so in the boost mode, we neglect the input capacitor voltage. The approach that has been taken is neglecting the input capacitor voltage for the boost mode, and for the buck mode, the output capacitor would be neglected. So, so we will obtain different small signal models for both the boost mode and the buck mode. So this was context of the boost mode, and pretty much the entire same thing has been done for the buck mode, and the final transfer function that we have got for the buck mode is this one. Right. Once we have the transfer function, the next step was to input the parameters within the transfer function and then obtain the and to design the controller for it. And as Neha mentioned, we have chosen PI controller for that purpose. And in order to calculate the PI case, we have used the Zeiger-Nichols method. So in Zeiger-Nichols method, what we do is we design our entire converter in the simulation environment, and then we perform the following steps in order to obtain the gains for KP and KI. Since we are designing PI controller, so we need the proportional and the integral gain. In order to do so, the first step is to design the entire converter in the simulation model, and then the controller as well. And for that particular PI controller within the simulation, we set both the KP and PI to be 0. And then we start gradually increasing the KP gradually or the proportional gain, and then we obtain the output whether we are getting sustained oscillations or not. When I say sustained oscillation, I mean the harmonics should not be out of order and should have the same frequency throughout. So as we gradually increase the KP and the sustained oscillations are received, so we note that value of the KP, and that is called the KCR or the right. And so the value that we have obtained the sustained oscillation for we note that value, and that is called KCR. And corresponding to that, we check the period of that sustained oscillation. So we have two parameters now. The first one is the gain for which the sustained oscillation was achieved, and the second is the period of the sustained oscillation. So these two particular parameters would help us find the gains for KP and KI using this particular table. So Zeiger-Nichols method uses different method in order to calculate the PI gain. For example, if this is one of the particular table for the PI only, then we have the PID, different table for PID. Also, Zeiger-Nichols method also works for the frequency response. Its step response. So all of those are different. So the particular one that we chose was this one, where we first find the sustained the period and the gain for the sustained oscillation, and then corresponding to this table we find our KP and KI. So here the KP is the gain that we initially obtained for which the sustained oscillations were received, and that PI was the PCR was the time period of the sustained oscillation, and corresponding to PCR we can find out integral gain KI using this formula right here. Right, so this Zeiger-Nichols method was used to calculate the gains for the PI, and corresponding to that, we then we ended up with the final controller right here for the boost mode, with the gain of the Zeiger-Nichols method gave us the gain of KP for the boost mode to be 0.0001 and the KI to be 0.6. Once we had this controller and this corresponding transfer function, so the transfer function that we previously obtained for the boost mode, once we input these particular values in context of electric vehicles within the transfer function. So this was the specific transfer function that we got. So we have the transfer function without the controller, we have the controller as well, and when we multiply these two, we get the closed feedback to right, and corresponding to this, we have the loop locus. So this loop locus design is for the open loop without the controller, and as we can see, we have the 0 in the right half plane. So the system was inherently unstable. In order to stabilize this open loop unstable system, we have to introduce this controller for the gains for which were calculated using Zeiger-Nichols method. And once we did that, the stability of the controller can be studied using this Bode plot. So for the open loop, the Bode plot can be seen in the which was unstable, and these two tables that we are seeing is to inform this stability pattern and for the closed loop system that is with the controller. So for the both of them, it's so that the closed loop stability is there for the controller, and with the gain value 5.9 which we found that was helpful in suppressing the reverse overshoot that we are getting. It was reducing the settling times of our system, as I was showing the difference. It was also avoiding large overshoots, and it was and the lifetime was also reduced using this design controller. Right, and the entire same thing that we have done for the boost mode was repeated for the buck mode with different gains that were calculated using Zeiger-Nichols method to be AP to be 0.02 and TI to be 1.2 for the buck mode. And similarly, we had the previous transfer function using these parameters. And once we multiply it with the controller, we get the closed loop control transfer function for which the same analysis of the root locus and and polyplot was done. So buck mode was in buck mode the system was inherently stable because there was no zero. This is the open loop response of the buck mode. So as you can see, there is no zero in the right half plane and was inherently stable. But in the open loop, the problem that we had was that the gain margin were very small. So when we are designing controller, we want these parameters to be as large, well, not as large, but sufficiently large to control the system. So although the open loop in buck mode, open loop response was telling that in the buck mode without a controller is inherently stable, but we still introduce controller using Zygote-Nichols method in order to increase the phase margin and the gain margin, and it can be seen that phase margin was increased up to 103, and which was relatively less without the controller and this. And then finally we have the closed loop stability to be true. Right, so this for the buck mode, and then finally once we have designed the controller and we have the simulation in place, these were the parameters, as I said, were selected in context of the electric vehicle. So ideally in electric vehicle we do not use non-isolated converter, but we did find some references in which converters were designed. But again, those were not in the context of actual electric vehicle, but some paper reported that they are performing this work in context of electric vehicle, and they choose these parameters to be simply replicated those parameters with the boost period with the power rating of 20 kilowatt, which is ideally not the case for non-isolated converters, because non-isolated usually work on low power ratings. So we have these parameters, and this is the entire setup that we did for to obtain the final results. So in this you can see that right, and from that particular setup we have finally these results. So we performed two test cases for a designed setup. The first one was the bidirectional mode, where we were switching between the buck and boost mode, and the second test case was for the load variation. So for bidirectional mode, we can see that this basically battery parameters, the voltage of the battery, the current of the battery, and the state of charge. So for the boost part, which is having from 0.02 it is the battery is discharging because it is running in boost mode, and as soon as we manually turn the mode from boost to buck, it starts charging. The battery starts charging, and the state of charge starts increasing, and the current is now negative because the battery is being charged, and the voltage essentially increases because we are now the charging voltage greater than the discharging voltage. And at this instant, we can then switch from buck to boost mode again. And as you can see, most of these overshoot are the minimized overshoot because before that, the settling time in the overshoot were far greater. So these results are with the controller that we have designed. And so these were the results for the battery, and these are the results for the load at the output side. You can see for the first part where we are running in the boost mode, the load that we have designed was at 450 volt, right? So it was at 450 volt in the boost mode. The voltage is maintained at 450 volt because of our design controller, and for the buck mode, since we are using an ideal for the buck mode, so the voltage is steady throughout the buck mode, and then when we enter the boost mode again, you can see the transitions again because now the ideal voltage source that we have is disconnected in the boost mode. And lastly, these are the inductor results that we obtained for the bidirectional mode. So we only studied them to see whether our calculations were valid or not. So we looked at the voltage, the upper limit and the lower limit of the voltage, and also the peak to peak current in order to verify our calculations. So we don't have the calculations with us right now, but we only use these stuff to validify our calculation, and it did validify the hand calculation that we have performed. Right. So after the bidirectional mode of buck boost transition, we have the load variation test case where what we did is we increased the load by 50% by changing the output resistance, and for that that transition happens at 0.03 second. As you can see, the state of charge, the slope for the state of charge decreases further as soon as we decrease the load, and similarly the current drawn also decreases and the voltage increases because now the load is at it is reduced by 50%. Yes. And so, we had to find some of the parameters, for instance, and others. We had to do them, but for this particular study, we did not did them, but it reduced the margins into but then in this separate study, where we are coming to looking at with and without how our results are.
Cannot say it's separate study. You must have जब हम डिजाइन करते हैं उसका जो लोग तो ये होगा इसका लोग स्टेप अगर आ रहा है तो how where the control is needed response to that change. How fast is your controller or get to the game instead of the voltage. It's not the separate.
Right, so that were the battery parameters, and this is the load variation that we have. So the voltage is still stabilized because of the design controller. After this, a little overshoot at 0.03 seconds, and the current is obviously reduced because load is decreased by 50%. And finally, we have the inductor. Load is that is and these again are the inductor parameters that we just have analyzed to match our calculations, and for that as well the peak to peak current and the upper and lower levels of the voltage were in accordance with the calculation that we have performed. Right, so with that, we would now start with the study of DC isolated particles.
सॉरी मैं आपकी बात काट रहा हूँ। ये आइडियल डीसी टू डीसी आइसोलेटेड की बात है ना, हमने प्रैक्टिकल आइसोलेटेड आइडियल नॉन आइडियल बनाया हमने या नहीं? मुझे आपकी आवाज नहीं आ रही। जी अब आ रही है।
अच्छा सर, तो आइडियल हमने नॉन आइसोलेटेड हमने नॉन आइडियल करा था क्योंकि हमें उसकी मैथमेटिकल मॉडलिंग वो नॉन आइडियल के टर्म्स में मिल गई थी, लेकिन आइडियल की आइसोलेटेड की जो मैथमेटिकल मॉडलिंग है उसमें हमें काफी मुश्किल हो रही थी, पेपर्स वगैरह भी नहीं मिल रहे थे, तो फिर देन वी थॉट दैट वी विल स्टिक विद आइडियल वर्जन ऑफ दिस।
ठीक हो गया, मैं बस अपनी कंफर्मेशन के लिए था। ठीक है, प्लीज कैरी ऑन। थैंक यू, गुड जॉब। और थोड़ा सा माइक नीचे की तरफ करें, मुझे जरा आवाज काफी एको के साथ आती है। पहले से भी चली गई है।
अच्छा,
आप बेहतर है।
अच्छा, so starting with ideal DC isolated parallel converter की study, this is our ideal DC to DC isolated converter, where we have the transformer and we have 8 switches in total, 4 on this side, 4 on that side. इसमें फिर ये होता है that S1, and for example, if we are in boost mode power flow, then the main pulse is sent to S6 and S8, and then its shifted version is sent to S5 and S7, and then S6 plus S8 का जो inverted version होता है वो जारी है S2 and S4 को, and then the shifted versions which were sent to S5 and S7, their inverted versions are sent to S1 and S3, right? And then we also have the V bus and the battery, obviously, and the input capacitor and the inductor, right? So moving on, this was a schematic of the design, and this is the simulation of that particular design, where we have the battery, the inductors, and the whole MOSFETs and the switches, right? Moving on, this is the controller part of that simulation. This was the whole converter. This is the controller where we get gate pulses, gate 1, gate 2, gate 3, and gate 4, which are basically these. There are 4 pulses generated because 2 gates are getting the same pulses. So we have 8 gates to power, and and like 4 pulses jari because 2 of them are getting the same, right? And in this particular schematic, this is the controller. We have our boost controller and our buck controller, where the switch decides the controller we are currently operating in, depending on the mode that is selected, and then using the 64-bit conversion and the duty cycle generator. Then this Z to the power minus 32 is basically generating a phase shifted version of the original pulse, which is this one, right? And this pulse is not and sent to gate 4, and its original is sent, where is the original sent? Right. Acha, हाँ, sorry. The second one, gate 2, and then we have gate 1 and gate 3, जिनको एक main pulse जा रही है और एक को not होके जा रही है, right? So then we come to the small signal model of the isolated bidirectional, which was also there for the non-isolated bidirectional, but this is for the isolated, right? So isolated में एक तो आपको ये difference नजर आ रहा होगा कि we weren't able to model the non-linearities of the circuit. Therefore, there's only the inductor, there's the resistance and the capacitor without their ESRs and ESLs. And so these are the state space equations that we got from the book for the small signal model, right? And using these equations and this conversion formula for generating this transfer function, we have our GVD for the boost mode, and then similarly, moving on, we have the small signal model for the buck mode, and this small signal model for the buck mode generated this particular transfer function, and then this transfer function. So now we have the buck mode transfer function, which is GVD buck, and then we have the boost mode transfer function, which is GVD boost. Both of them were derived using this particular formula and using the del X and del Y equations, which we got from the book, right? So moving on. Similarly, we made use of Ziegler nucleus method over here also, which SN explained. So, वही procedure है, KP and KI is set to 0, and then they are in KP is increased until we reach sustained oscillations, and the particular value of KP at which sustained oscillations are achieved is called K star, and then this KCR and the particular period that at which this KP is achieved is PCR. So KCR and PCR की value use करके we find PI and KP, and PI is basically KP over KI. So we get our KI की value and KP की value, right? Moving on. So these are the results. This is the transfer function so this is our KP and KI for the boost mode. Just we have so this is KP and KI for boost mode, and this is the KP and KI for buck mode. And then using these parameters, we generated these GVD boost and GVD boost and GVD bug, right? And GVD boost and GVD bug जो अभी previously I explained जो small signal model से हमारे transfer function आए हैं उनसे ये दोनों transfer function using the parameters that we have used ये दोनों set हुए हैं, right? So once we have this and we have an PI, we multiply them and then we get the GPI boost and the GPI bug, right? And okay, so now we have our GPI, our boost root locus and our root locus and its magnitude and phase response. So as you can see that using the MATLAB stability criterion, we have achieved that yes, our system is stable, is closely stable for boost mode, and similarly this is for the buck mode. Moving on, Zohaib.
So basically now Hmm? So now this slide is similar to the isolated slide, non-isolated slide, where the block diagram is the same. Only the difference is that the values of the capacitor, inductor, those things are different. And the moving on, these are the results. So this is basically the discharging and starting characteristics, where you can see the discharging is from around 3 milliseconds, and charging starts from around 5 milliseconds to 8. Sorry. Charging starts from 0 to 3 milliseconds. Charging or 0 to 5 milliseconds, 8 milliseconds, और charging जो है वो है 3 milliseconds से 5 milliseconds. Now basically the SOC, as you can see, is increasing when it's discharging. While in charging, it is increasing. This behavior of the SOC is because of the characteristic curve of the battery, where it enters into the acceleration. And this is basically the load voltage. So you can see they have load voltage to 200 volts. The load current is around 12 amps for the charging and the discharging. This is the inductor voltage, where you can see the gate. So these results were verified with the theoretical calculations. And although the calculation and this is the inductor and the inductor voltage will have been verified. Now this is basically for the load variation, where the 50% load has been. First the load was around 60%. After that the load was increased to around 25 ohms. It's like around a 50% increase in load. And load voltage, you can see the current has been changed. The load, the current increases and the voltage there remains almost the same. This is the inductor voltage and the inductor current. I think this was verified in mathematical that we have done. Now coming on to this, this is the paper we have submitted, which has been accepted. And icon की बात icon का
Right, so icon की paper that we have also submitted, but सर उसकी बात आपसे करनी थी ये कि हम लोग उसकी डेडलाइन कब तक हो गई है 31st तक हो गई है, तो सर इसका ड्राफ्ट जो है उसमें अगर भी चेंजेस करने हैं और तो आप हमें बता दें ताकि हम उसको रीसबमिट कर पाएँ. और सॉरी फॉर सबमिटिंग विदाउट आस्किंग योर परमिशन. I don't know. Right. So और फिर इसके अलावा we also had to tell you that PADG जो है उसकी deadline is on 22nd. So उसका भी draft is ready, and if there is any changes that are to be made, do let us know. We will also be adding the changes that Mr. Aminda just suggested. Right. And moving on to the app for our mid-evaluation that we had achieved. And as you can see, there were some yellow and some red blocks at that time, but now we have been able to achieve all of them. The mathematical modeling of isolated boost has been performed, it has been tuned, and we have been able to submit the full paper of non-isolated and isolated. This is some of the conclusion and future work that is possible and has been final paper that is discipline and then have the IE confirmation, and then Similarly, the another main future work that is possible in our project is extension of this simulation to a hardware converter. This is being often like it's not confirmed, but right, and this is the work that
Yes, he is. Good job. Very nice, good.
he is.
He is online.
Can I ask you a question?
अच्छा जी, मुझे ये बताएं कि आप नॉन आइडियल आइसोलेटेड के अंदर कुछ काम कर रहे हैं फर्दर, या है प्लान या नहीं है प्लान में?
नॉन आइडियल आइसोलेटेड में ये था कि उसका फॉर द मोस्ट पार्ट जो हमारा क्रक्स था FIL FPGA लूप वाली सेटिंग, उस पे तो हम लोग उसके लिए रिजल्ट तो ले आए हैं, लेकिन सजेस्टेड के जो कंट्रोलर के हमारे पास कंट्रोलर एंड विद कंट्रोलर जो हमारे पास एक कंपैरिजन है उसकी स्टडी मिसिंग है, तो उसको हम लोग एक्सटेंड करके वी कैन टारगेट इन दिस आईकॉन कॉन्फ्रेंस दैट वी हैव मेंशनड। तो उस पे हमारे पास ड्राफ्ट भी रेडी है एंड दैट वी हैव शेयर्ड एज वेल, और उसकी हमारे पास जो हमने इनिशियल सबमिशन थी वो आईकॉन में करी थी, लेकिन वो होपफुली कि उसकी जो डेडलाइन है वो भी बढ़ गई है, सो वी कैन रीसबमिट दैट ड्राफ्ट विद द कंपैरिजन ऑफ द कंट्रोलर विद एंड विदाउट कंट्रोलर बेसिक रिजल्ट। तो उस पे हमारे पास एक पेपर वर्क भी फाइनलाइज।
नहीं, मतलब आप क्या एच ब्रिज को यूज करते हुए आप कंट्रोल कर रहे हैं नॉन आइसोलेटेड कन्वर्टर, राइट? प्रैक्टिकल केस नहीं, मुझे आपकी आवाज नहीं आ रही।
हमारी स्टडी है वो पूरी आइडियल पे है, इस वी हैव नॉट टारगेटेड नॉन आइडियल फॉर अप टिल नाउ।
हाँ, तो मैं बेसिकली यही पूछ रहा हूँ, क्या नॉन आइडियल पे जाने का प्लान है? क्या मतलब बेसिकली रोड ब्लॉक्स क्या है एग्जैक्ट?
नॉन आइडियल में हम लोग इनिशियली स्टार्ट विद नॉन आइडियल, लेकिन उसमें इशू ये होता है कि हमारे पास सेल्फ पे हमने काफी किया, लिटरेचर रिव्यू भी किया, काफी सारे पेपर्स की हमने ऐसे टारगेट करने की कोशिश की जिसमें उसकी मॉडलिंग मिल जाए। मॉडलिंग फॉर द मोस्ट पार्ट हमें नहीं मिल रही थी, एंड मॉडलिंग टू डू फ्रॉम स्क्रैच, उसके मैथमेटिकल मॉडल्स ऑब्टेन करना नॉन आइडियल के फ्रॉम द स्क्रैच वाज गेटिंग टू बी वेरी डिफिकल्ट। तो उसमें वी कैन लुक फर्दर इन द कमिंग वीक के कुछ एक्सटेंसिबिलिटी है टू मॉडल द नॉन आइडियलिटीज in the converter, अगर वो possible होता है, so that we can update our paper in regards to the non-ideal model. If not, तो फिर we would most have likely be sticking with the ideal scenario.
ठीक है, okay, got it.
Sir, any other question?
नहीं जी, not from my side. I'm good.
Dr. Shah also doesn't have any questions.
हाँ जी, क्या मुझे आप वीडियो क्यों दिखा रहे हैं?